So first thing I want to discuss is what I want to kind of do with the next. We've got 4 weeks left. Okay, so I want to discuss what I want to do with those 4 weeks. Okay, so I'm going to teach some stuff I taught last year, a little bit, and then I'm going to discuss how it relates to a kind of other areas. So the first part that I'm going to discuss today isn't really in the notes, but it's just kind of an overview of what we're going to do for the next 3/4 weeks. Okay. And then we'll do it. We'll do what we're going to do for the next 3-4 weeks. But I want you to understand what we're doing now and how that fits in to what we've been doing on Markov decision processes. Okay? So just start a fresh sheet here, and you don't need to copy down because you have the video, so you can get an idea from the video what's happening. So you don't need to copy down what I'm writing down. Okay? Okay. So what have we done so far? We've mostly been concentrating on Markov decision processes, because you can copy down if you want, but you don't need to. Yeah, don't feel you don't have to. Okay, so I just want to quickly overview one of the main points about Markov decision processes. Okay, so here in this kind of first setting, what we've been doing is you're in some state X. Okay, so that's state X, all right? And we've got several actions which we can take from that state, okay? So we might have action 1, an action 2, another action 3, okay? And then what happens is we take that action, all right, and we get some reward, okay? So we get a little reward R of A of X, okay? And I'm going to slightly change things a little bit. Now, normally what we've done is when we take an action from a state, we get a deterministic reward. But it could be random, yeah? There's no reason that we could, once I've chosen my action and from a state X, that it could depend on some randomness, yeah? Okay? And so normally when we have like random things, we have some sort of omega, yeah? Omega is like the outcome in your probability space. Is that okay? Yeah? Okay, and so here we're getting, given the action I take and the state that I was in and some randomness, okay, which belongs to some set of outcomes, okay, I move to some new state. Let's say I take action 2, I'll move to some new state which we've usually denoted by like x hat, all right, and then from there on out we follow some policy and it gives us some sequence of rewards, okay, so we sort of move around after that and we get some reward from state x hat for following some policy pi, okay? And so one of the crucial assumptions that we made when we were looking into Markov decision processes is that we sort of know the reward we're going to get, okay? Or we know at least the expected reward we're going to get, okay? So for Markov decision processes, so MDPs for short, so for MDPs, we assume we know R of A of X, which is the expected value of this random variable, yeah? Okay? And then what we did is we then kind of had some way of updating what's a good action based on what reward I get for taking action A in state X and from the rewards I get in the future, okay? And Bellman's equation was a way of kind of summarizing what is a good action given the instantaneous reward I get, this little r, plus the rewards I get in the future, okay? So, and we'd solve for an A star. So we try to find an action, okay, which would be the maximizer, okay. And, well, maybe you can help me. So I'm going to write down Bellman's equation now, okay. So Bellman's equation is the sum of the instantaneous reward plus the expected future rewards. So what am I going to write here? Okay, someone put their hand up. Everyone's really quiet. No, just me, leaving me hanging. Okay, so it's going to be R bar A of X. Okay? So that's here, that's the instantaneous reward I get, plus the expected future rewards. Okay, so if I had some discount factor, it would be like beta, and have the expected value. Given I'm in state X, and I take action A, I look at the reward I get from the next state onwards when I follow some policy pi. Okay? All right? So, we kind of need to know two things to evaluate this. So, if R is just some function that I've defined and found it to be the stationary reward for some policy pi, okay, then this corresponds to an algorithm called policy iteration, yeah? Policy iteration was an algorithm that we covered earlier, where you work out what the reward is for following a policy pi, okay, and then you update by taking the action that's best with respect to that policy. This is sort of going like, here, I follow action A, and then I follow a policy pi, okay? And if I choose an action that's the best, then it's going to improve on the previous policy pi, okay? So there's two parts to this. There's the policy evaluation and the policy improvement part when we had algorithms for these, okay? So the policy evaluation part was working out what this R x hat of pi is, and the policy improvement part was where we looked to find an action that was better for each state, okay? Now what we're sort of starting to move towards is sort of dealing with a kind of crucial assumption that we've been making the whole way through, and that is that we kind of know what the rewards are, okay? And we know what the movement of the stochastic process is, okay? So in the case of, say, when we were considering diffusion control, we were considering that we knew the mean, we were considering that we knew the variance of our diffusion process. And then our only job was to optimize, but we kind of like just averaged out all the stochastic elements of it, okay? So there's going to be sort of quite a bit of theory to deal with the case of decision problems and Markov decision problems where we don't know what the reward function is in advance, okay? So we don't know what R bar is here, so we don't even have a chance of finding the best of these amongst all the actions that we can take, okay? So what we're first going to start to deal with is dealing with understanding how to estimate these rewards and find the best ones, okay, in the case where there's unknown rewards. Okay, so we're going to look at this when the unknown rewards. Okay, and time depending, okay, we're going to look at how we can estimate this expected value here, okay, evaluate a policy, okay, when we don't know what the transitions are. We don't know, like, it's a Markov chain, it had a matrix P for doing calculations. We don't know what that matrix P is, how we're going to go about calculating this Rx of pi, okay? Okay, so unknown reward for a policy. Okay, so in particular, and I'll just sort of explain a little bit more what I mean by 1 and 2 here. Okay, so what we're going to consider first is something which we're going to call online learning, as you can see from the sheets of paper in front of you. Okay, so what's the idea? We're going to make a very, 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 what would be an almost trivial Markov decision process if we knew what the rewards were, but we're going to assume we don't understand actually what the structure of the rewards are, okay? And we're going to try to learn what the best action is, okay? So let's draw a picture. So before we were in some state X, okay, and we had some actions available to us, action 1, action 2, and action 3, okay? And I could assume that sort of every time I follow an action, I just return back to the state I came from, and then I take another action, okay? Each time I take an action, I get a reward for the action that I take and for the outcome, okay? And the outcomes going to belong to some set of outcomes, okay? So notice here, the state, I've ignored the state, there's no x here, so it's like a Markov decision process with one state, yeah? Okay, so there's no state anymore. Okay? Okay? And there's some space of outcomes. Okay? Right. So let's say I knew what the expected reward was from each action I take. Okay? What would you do? Okay, it's kind of easy question. So, like, the reward of A1 is 10, the reward of taking action 2 is 5, the reward of action 3 is minus 70. You just take, the maximum, so you go for A1 and get a reward of 10 each time, okay? All right? But the problem is we don't know what the rewards are. I haven't told you it's 10, I haven't told you it's 5 and it's minus 70, okay? You're just going to get maybe, and it could be random, okay? So you're just going to get some random reward each time, okay? And then your job is to figure out which one is actually giving you the best reward on average, okay? So that's sort of the problem of online learning, that you're going to try something out, an action, you get some reward from trying that, okay? And then you're eventually going to hone in on which is the best action, okay? Okay. And the other thing I'm going to add to this to make it even more complicated is, well, one thing you could do is you could say, like, let's say there's some probability distribution to the rewards. Let's say it's the first arm gives you 20 with probability half and 0 with probability half. So that gives you an average of 10. Okay? And you could assume a distribution, a probability distribution you need to estimate. I'm not even going to do that. I'm just going to say there is some completely arbitrary sequence of outcomes that are going to happen. And it could be probabilistic and it could be non-probabilistic. It could be an adversary who's sort of working in the background to give you the worst possible reward possible. Okay? So it works in a very kind of robust set of environments. Okay? A typical learning problem, okay, which we'll cover, is called the multi-arm bandit problem. And did I mention to you about multi-arm bandit problems before? Did I mention about that? Okay. So this is a kind of typical online learning problem. Okay. You're in a casino, okay, and in front of you in the casino are several slot machines, okay? Now, sometimes a slot machine is called a one-arm bandit, okay? And why is that? Because it's got one arm and it steals your money, okay? So that's okay? And so the question when you've got multiple slot machines is called a multi-arm bandit problem, okay? So now, you're faced with, I don't know, 10 or so slot machines, and you want to make as much money as possible, okay? So you've got to figure out which slot machine makes you the most money, or loses you the least, at least, okay? The one that gives you the highest expected reward, okay? So, what you're going to do, you're going to try out some of the slot machines, okay? And then you could try, like, uniformly at random for a long time, and then find that one of them gives you the highest expected reward, and then you stick with that one, for example, okay? Now, that might not be a very good strategy because you spent a long time exploring the different arms. Okay, so you spent a long time trying to get the statistical information you need to find the best arm. Okay? On the other hand, you could try each arm once and then go for the one that gave you the highest reward. Okay? That's not a very good policy either because, well, you haven't got a lot of data to base your decision off. Okay? So you can see here there's a trade-off. Okay? This is sometimes called explore-exploit trade-off. Okay? The idea is you want to explore to try and find out the distributions and learn which is the best arm, but you want to exploit, you want to move on to the best arm as quickly as possible in order to maximize your money. Okay? So that's a typical type of online learning problem. Okay? Another type of learning problem is, let's suppose these actions, action A1, A2, A3, are basically three, portfolio managers. Okay? They're investing your assets for you. Okay? And they're giving you advice where you should put your money. Okay? And at each round you get some reward from either portfolio manager. Okay? And then you've got to decide how much of my money should I invest in portfolio manager 1, 2, or 3. Okay? So each round you get all the information about the rewards, but you want to essentially concentrate and distribute your money over these. Okay? Again, that's another type of online learning problem. Okay? So that's the kind of problem that we're going to consider. So there's two settings there. One is a kind of expert setting, one where we've got 3 portfolio managers who are going to tell us what rewards they're giving to us, but we've got to decide how to invest our money between them going forwards. The other was this kind of bandit problem, where we only observe the reward I get from the machine I play, but I don't know what would have happened if I tried the other machines. Okay? Okay, so that's the kind of online learning part, and that really concentrates about figuring out what's going on with this reward I get for taking an action. Okay, so we're just sort of considering the simple setting of just figuring out what this is. Okay, when it's an unknown function, when I don't know the average expected reward. Okay, the second part, which if I get time, will concentrate on this part. Okay, so let's say I don't know the way that my Markov decision process navigates, okay, or the expected reward of that, okay. I only have access to, say, some environment, say, to simulate it. So you could look at like a financial event scenario generator and things like this, okay. So you could try and generate samples and then try and get an idea of what your expected reward of your policy is, okay. And so the second part, I should have a number 1 here. 1. And then 2, the second part that we'll try and consider is more on policy evaluation. Okay. And so here, what we want to do is we start at some state and we want to get an idea of what the reward I get from that state when I follow a policy pi is, when I just have to generate sample paths of my Markov decision process. Okay? So we're going to focus on evaluating the expected reward of x hat from some policy pi. Okay? Notice when I've got those two things together, okay, when I've got an idea of how I can explore different actions and how I can evaluate different reward functions, I can essentially get rid of the idea that I don't know what the probability distribution is of rewards and I don't know what the transitions are, okay? So once we've gone through those bits, we'll have a very basic algorithm for doing something called reinforcement learning. Essentially, the combination of online learning in this way and evaluation of policies in this way is sometimes called reinforcement learning. Okay, so it's kind of the area of Markov decision processes where you don't know the expected rewards and you don't know the probabilities of transitions, but you need to estimate them. Okay, all right. So if I had time, which I probably won't, is that reinforcement learning okay, considers Markov decision processes when the distribution or the transitions and rewards are unknown. Okay, and if I had another lecture course, so we could do that as well. There's quite a bit we can kind of do kind of a little reinforcement learning algorithm. If you're doing I'll probably write sort of 3 or 4 essays this summer for the financial maths MSc. So if you want to do more reinforcement learning and kind of pick up where we left off from here, then you know, you can pick one of those and we'll do some reinforcement learning stuff for finance. Okay. So there's plenty more that one can do there. So, but that's basically what we're going to do in terms of material. Okay. And then what are we going to do in terms of homework and in terms of preparation for your exams, which is equally important. Yeah. So probably what I'll do is I'll prepare one more kind of example sheet for you to try out on the online learning material. Okay, and you can have a look at that, and that gives you good practice of the material that we'll cover, at least as far as the exams are concerned. Okay, then I'll probably give to you last year's exam sheet. Okay, and then in the last week of class, we'll go through the exam and how to solve it and how to do everything. Okay, so regardless of where we get to, the last 2 hours at least we'll be going through the final exam, and you should try to do it before that as well so that you've got an idea, okay? So the best practice for this year's exam is probably last year's exam, because this course didn't exist before that. So we'll go through that, okay? Okay, and you can also ask me lots of questions like, Neil, what's going to be on the exam? And I'll tell you, well, it might be this and it might be that, and, you know, kind of, I don't mind giving subtle hints, but I obviously can't tell you what's on the exam, but I can sort of give you an idea of what flavour of it's going to be, okay? Yeah? Okay, good. All right. Are there any questions? Okay, fine, good, okay. Right, okay, so we'll start to go through the material stuff here now, okay? Okay. Okay, let's just zoom in here. Oh, and it's not letting me move very much. Okay. Well, that'll have to do. Okay. So the first couple of paragraphs here are just describing, in less words, what I just said in those pictures, okay? So we're going to consider a set of problems that would be trivial, okay, if it were a Markov decision process framework. We just have a set of actions, we choose the one that gives the maximum reward. Okay, so we just choose the action A1, which gave us a reward of 10, okay? So here, there are going to be a set of actions, A, okay, but the state of the system doesn't really evolve in the same sense that it did previously, okay? Thus, if we can consider a Markov decision process setting, we'd always choose the action with the highest expected reward. However, this ignores an important feature that we have thus avoided so far, and that is that the distribution of rewards is specified and known to the algorithm, to the Markov decision process, okay? Even in the simple setting, where the state doesn't evolve, there's considerable challenges when we do not know the distribution of rewards. Okay, so if we don't know the distribution of rewards, it's actually quite a tough problem. Okay, that's ignoring the fact that there's some state of the system X that moves around on the Ludo or lottery, you know, or snakes and ladders board or whatever. Okay, essentially we need to learn statistically or otherwise the distribution of rewards, and then based on the information gathered so far, move towards the optimal decision. Okay? So So now I'm going to kind of explain a framework for considering these things, okay? So we're going to start to develop a framework for looking at this setting, okay? So we consider the problem now of learning the best action amongst a fixed reference set, okay? Although our modeling assumptions are quite a bit different than what's been previously, we're going to try and keep the notation as similar as possible to previously, okay? Okay, so we're going to consider the following setting. We're going to have a set of actions, A, here, okay, just like before. Can everyone see the yellow okay there? Is it it's a bit, I can't see it that well. I'm going to change the colour, wait. Where am I? That one. I don't know why, but my screen doesn't come up very well here. Okay. It's kind of there, the button, but it's not giving me it. Okay, anyway, doesn't matter. We're going to have to go yellow. Sorry. This is a problem with these things. No, it's just not going to work. Okay, it's going to have to be yellow. Sorry, guys. Okay. Okay. So we consider actions A, and we're going to have outcomes omega. Okay, we can interpret omega, like I said, as in like a probability space. Okay. It could be the outcome of some random event that determines what the reward is. Okay? After choosing an action A and an outcome omega occurring, you receive a reward RA omega. Okay? And I'm going to assume, at least for now, that the reward belongs to some interval 0 to 1. So it's positive and it can't be bigger than some fixed maximum, which I've arbitrarily chosen to be 1. Okay? And we're going to assume that the set of actions is finite and of size n. Okay, so there's a finite number of actions. So it's like n gambling machines in front of me. Okay? Okay, so what's the policy in this setting? It's kind of the same thing as before. I look at what are the past outcomes that have occurred previously, and I look at what the past rewards are that have occurred previously. Okay, and that's the information that I have in order to base my decision. Okay? So over time, outcomes omega t occur from time t equals 1 to capital T. Okay? And we don't currently assume, at least currently, and we can add that assumption to get slightly different results, we don't currently assume that there's an underlying stochastic process that determines the values of Wt. So I'm not assuming like the W's are IID random variables. There could be dependence between them. It could be like a game theoretic setting where someone's trying to minimize my rewards in order to maximize their game. So it could be a gambling setting as well. Okay? Anyway, okay, so we could consider this in a game theoretic setting also. Okay, so the values of omega t could be chosen arbitrarily. Okay, at each time t, a policy pi chooses an action, which I call pi of t. Okay, as a function of the past outcomes and their rewards. Okay. So I just look at what happened in the past, I looked at the rewards that happened, and then I make a decision as to what action to do at the next round. Okay? Okay? All right, so that's it. So I go up, I choose a gambling machine, I pull the arm, it gives me a reward. Okay? I also see what would have happened if I got the rewards from the other gambling machines as well. Okay? So that's the kind of setting we're considering here. Okay? All right, the total reward by time capital T of a policy pi is just the sum of the rewards of my policy. Okay? So that's very similar to the Markov decision process framework. Okay? Now, slightly different notion is the regret of my policy. Okay? The regret of a policy is which I've written as kind of script R. I struggle to find a good notation for regret, regrettably. So I write R, G, and then T for the time that it's been over. Okay, that is the difference between the best reward, okay, if I chose some fixed action A, all right, and the reward that I got from my algorithm, or my policy pi, okay? And I've added an expectation in here, okay? That expectation is because I'm allowing it that I could have a randomized algorithm, okay? So it could be that I choose, there's 10 gambling machines and I choose one uniformly at random, okay? I do that as my way of discovering which one's the best gambling machine, okay? So I'm taking an expectation over the randomizations that I take in my policy, okay? So let's think a little bit about what this regret means. So if I maximize the reward that I get by time t over all the actions so far, that is the best gambling machine. So if that action was which gambling machine I use, okay, the one that's maximum is the one that I could kind of look at after t units of time and say that one gave the most money out, okay? Of course, I didn't know that in advance. I didn't know which of these 10 gambling machines was going to give me the most money, okay? But after that time, I can say, well, this one was the best one, okay? And in the meantime, I can look at how I performed in using my policy compared to the best gambling machine. Okay, so I kind of moved around between the different machines, and I got some money. And I can look, how did I do compared to the best? Okay, that's what that's looking at. Okay, so that's like, what is the best action, and how did I compare? How was my reward compared to that? Okay, is that okay? So you can think of the regret. The bigger this number is, the bigger I regret not playing the best machine. Okay, and the smaller my regret is, or the closer to zero, or even potentially below zero, my regret is, the more I'm performing better than the best machine. Okay, all right. Okay, so some comments on that. So it's good to think of an outcome as an outcome from a probability space, though we don't assume that, okay? But you could think of it that way, all right? And indeed, sometimes we can assume this, okay? All right. It's good to think of rewards, R of t, in the same way we consider the rewards from the Markov decision process framework, okay? Although we don't assume there's a state anymore, so there's no x. Okay, so we've got rid of x's. Okay, so the kind of Markov side of things has gone away. Okay, the regret compares how well our policy compares to the best fixed reward. Okay, so I'm not comparing a policy against the best policy. Okay, so I'm not comparing me moving around against the best way of moving around. I'm comparing me moving around compared to the best single machine that I could have chosen, the best single action that I could have taken. Okay? So that's something to make sure you understand, that it's actually what we're considering is really a weaker notion of optimality in some sense than what you might think. So a policy could be something which changes in an arbitrary way between the different machines. Okay? And it's in fact impossible to do as well as that. Okay? But if there's one machine that is the best and that's a good machine to go to, we're going to do as well as that, okay, if we get low regret. Okay? Okay, so that's what that says. A regret of 0, or asymptotically 0 as t goes to infinity, so on average, the average regret going to 0 as t goes to infinity, means we're doing as well as the best fixed choice, or doing as well on average as the best fixed choice. This is sometimes called Hanan consistency. Okay, so sometimes in the literature, this will be called Hanan consistency. Hanan was some statistics professor in Harvard in the 60s or 50s or something like this. Okay, so the original result of this type was called like Hanan-Gadun theorem or something like this. It's like 1955 or something like this. Okay. Okay. So we're interested in how a policy pi performs in comparison to the best fixed policy A. Okay. Notice this is a weaker assumption than comparing to all policies, which I just described. So this weaker notion of optimality means we're making a slightly weaker comparison, and that's why we're considering the notion of regret. Okay, so when we're considering an MDP with the states and we know all the rewards, we're looking at the optimal over all policies. Okay, whereas here we're looking compared to the best fixed action. Okay, so as you know, there are things like policy iteration and value iteration where we see that we can kind of treat them as the same thing. Okay. So one result that I'll prove to you is that says, well, we've got this notion of regret, Okay, what is actually a kind of good behavior for the regret? Okay, what is sort of the best we can do, at least if we don't know the statistical structure of the outcomes? Okay, so this gives, so the first thing we're going to prove is a lower bound on the regret that says this is about how well you could do with any algorithm if we don't know the statistical distribution of the rewards. Okay? And if we don't assume there's an underlying statistical distribution. Okay? So let's consider the following case. There are two outcomes, okay? And that should say omega. There's two outcomes that can occur, either A or B. Okay? Left or right, A or B. Okay? And there are two actions that you can choose, A or B. All right? So you can think of this as like a really simple paper, scissors, stone, but without the stone. So just paper, scissors, yeah? Does everyone know paper, scissors, stone? We could do this with three actions and do the same proof. It's basically you drop a match, whatever, you get a reward from matching or not matching with the other person, okay? So here we're considering a situation where if the environment chooses A and I choose A, then I get a reward of 1, okay? And if the environment chooses B and I choose A, I get nothing. Okay? And vice versa. If I choose B and the environment chooses B, I get 1. If I choose B and the environment chooses A, I get 0. Okay? So if I match, I get 1. If I don't match, I get 0. All right? Okay? Now, if I assume, for now, that each outcome, okay, this A or B chosen, that should be an omega here. If each outcome is chosen uniformly at random from A and B and is independent, then you can show that whatever policy I choose, the regret of my policy is always going to be bounded above by square root of t. Okay? So after t units of time, my performance and compared to the best expert is around square root of t. Okay? Notice, even in that case, if I divide by t here, and look at the average regret, if I divide by capital T the amount of time I've been running things for, okay, notice that this is going to 0. This is equal to a constant times square root of t, which goes to 0, okay? So the best algorithm, in principle, can still get a regret that vanishes to 0 on average. So it can still be Hanan consistent, okay? But you're also going to be about square root of t away. That's the best you can do. Okay? So let's show that. Okay. So if I choose A, what's my expected reward under this? Given the what do I expect to get as my reward? So the person I'm playing against is just going to choose uniformly at random. Okay? And I'm going to choose A. What's my expected reward? Yeah, a half. Yeah? So it's either 1 with probability of half, they choose A with probability of half, or they choose B with probability of half. Okay? And if I choose B, the expected reward is a half. Okay? In fact, no matter what I do, the expected reward is a half. Yeah? Okay? So, my expected reward after playing for T rounds of whatever policy I happen to have chosen is what? Well, each round, my expected reward is half, and I've been playing for T rounds, so it's T divided by 2. Yeah? So I've been playing for T rounds with an expected reward of half. I've got T over 2. Okay? Okay. Further thing I can note is if I look at the reward for the policy that chooses A all the time, and I add it to the reward that chooses B all the time, okay, but either A wins or B wins, okay? So the sum of the reward from A plus the sum of the reward from B is 1, because there's a reward of 1, and 0. Okay? So either A gets 1 and B gets 0, or A gets 0 and B gets 1. Okay? So if I do that t times, then I've got a total of t. Okay? Okay, that's that. Okay? So, now, let's look at this. So we've got the reward from A is going to equal the average of t over 2 plus some error, which I'll call like epsilon t. Okay? I just define an error. Okay? And then I know from this relationship that reward from B is equal to t over 2 minus epsilon over t. Okay? Okay, so now, effectively what we've done is, let's say, at each round, the probability of A being correct is a half. Okay? And let's say I've run it for 100 rounds. Okay? Then the expected number of wins I've got is 50. Okay? But then you've always got some error around that. Okay? And if I let t, the number of trials that I've done, get really, really big, okay, what does that error look like? So let me put it this way. I toss a coin 100 times. Expected value is 50, yeah? The error about 50, what's the distribution of that error? Let's say I do 1,000, 10,000, a million coin tosses, okay? If I do a million coin tosses, I get approximately 500,000 heads. That's what I expect to get. But it's never going to be exactly, well, it's quite unlikely to be exactly 500,000, okay? The error around that is always a normal distribution, or approximately a normal distribution, yeah? Okay? Because if I sum up IID things, we've got the thing called the central limit theorem, which says sort of the error about the mean of independent trials is approximately normally distributed, okay? So what I'm saying is that guy is going to look quite normally distributed, okay? So by the central limit theorem, and I have to be a little bit careful because we have to rescale in the right way. The error is about square root of t times the number of trials, and I'm gonna, if I let t get really big on that, it's gonna go to something that's approximately normally distributed with the mean of 0 because I've taken the mean off, and then I have the kind of variance, which is a half for a Bernoulli random variable. Okay. Which I think it's a half. It could be a quarter, I forget. Okay. All right. Does that make sense? This D means in distribution. So it doesn't actually, in the distribution of this guy is going to approximately be a normal distribution as the number of trials gets larger and larger. Okay? So now let's look at the regret. The regret of my policy pi, okay, if we remember from the definition, is the maximum reward A, where A is equal to A or B, minus the expected reward of my policy. Okay? Which then is going to give me, well, that's equal to t over 2 plus epsilon, and that's equal to 2 over 2 minus epsilon. And I didn't say epsilon's positive. Okay? And I'm going to minus off this, which is t over 2. That's equal to t over 2 plus minus epsilon over t. Okay? So what this resorts down to doing, oh, sorry, I'll move that up a little bit, okay, is I've basically got t over 2 plus or minus epsilon minus t over 2. So I'm going to end up with plus or minus epsilon, okay? So if epsilon is positive, I'm just going to take epsilon, because that's going to be the biggest number. And if epsilon's negative, I'm going to take minus epsilon, because that's going to be bigger, okay? I'm going to take whichever is bigger, plus epsilon or minus epsilon, okay? So that's equal to the modulus of epsilon, okay? So in other words, if I divide by square root of t on this guy, it can never get bigger than the modulus of a normal distribution, okay? So notice, let's just say I divide by square root of 2. Well, I'll do it here. So I hope you've got space. I don't have much space, but you're probably right smaller than me. It goes to the expected value of the modulus of a, well, it's going to just go to the distribution of this guy. It's going to go to the modulus of a normal distribution. Okay? So no matter how well I do, I can never get outside of square root of t. Okay? So that's giving me an idea of how fast we can learn, essentially, in this setting. Okay? So if I'm worried about the regret, how well I'm doing compared to the best arm, I can never do better than being about, after t trials, I can never do better than being about square root of t away from the best arm. Okay? So that's saying, like, I've got 10 slot machines, I do 100 trials, let's say. I gamble £100. Okay, square root of £100 is 10, so I can never be within about 10. Okay, of the best machine. Okay, then I decide to spend £1 million. Okay, playing slot machines. I've got real bad gambling addiction. Okay, I can never be within 1,000 of the best. I can never do better than say 1,000 within the best slot machine. Okay, does that make sense? Okay. But that explains how well I potentially could do if I could think of a good policy. I can't do better than after 1 million trials being within 1,000 of the best machine. Okay? £1,000 of the best machine. But we need an algorithm to do that. So what we'll do next in the next half is give an algorithm for actually playing the different machines and achieving that bound. Okay? So that's the best we can do. Now let's give something that does the best we can do. Okay? So we'll do that after the break. Okay? So we'll have a 10-minute break and then